Hello again. I have not so far received any reply, so let's continue. There was a mistake in that derivation. If you just find it out and be the first, you get a prize. And now I will start another topic, and that is topic which is connected to forces. There is one general rule that states the force affecting electric charge. This effect could be done in two ways. That could be due to electric or magnetic field. Now, the force that affects an electric charge Q is given by two components. We know the first one because that has been a definition equation for electric field strength. So first we have the electric field strength, and the force is of the same direction here, just it could be in the opposite sense for negative charges and positive sense for positive charges. So this is already known, but then there is a second component, and this looks a bit tricky. It's a vector product of the velocity of the charge, with which it moves within magnetic field. Now there is a vector product, and I would like to make a short comment. Both parts of this equation are used, for example, in colliders. The big collider in CERN uses both parts of this equation. First, it uses the second part to bend the trajectory of moving particles within the collider. Watching this part of the equation, we can say that the resulting force at any moment is perpendicular both to the magnetic field and to the velocity of the particle. But now if you have a particle and you put a force on it which is perpendicular to its current velocity, you will bend the trajectory, but the particle would not change its velocity as to the magnitude. So you will not change the energy of the particle. It would run at the same speed, just bend its trajectory. This part of force makes no work. No work is carried out by this part of the force, so magnetic field can change the direction but does not provide any energy or any work. Well, the electric field, that's another story. The electric field can speed up the particle, and that's why within the accelerator there is a number of electrodes that provide for acceleration. This is the complete equation, and I wanted to start with it, but at the beginning we would start with the first part. So what is the force carried out by electric charge? We have been discussing a capacitor last week, so that's something that has two electrodes. Let's make it very clear. We have a big capacitor with two electrodes of constant cross-section. The distance between those two electrodes is small d, and it's much smaller than any of the other dimensions of those two parallel plates. So it could be, for example, made of two plates of the same cross-section. We would have some voltage over the capacitor, and as the field inside the capacitor is homogeneous due to the fact that those electrodes are very big, we would get an electric field strength E inside, which is homogeneous. That is, it points in the same direction at any point of the capacitor, and it has the same magnitude. So it's a homogeneous field. Now the question is, what would be the force or the pressure that this field exaggerates on those two electrodes? Well, the first reply is the force would be attractive. It would attract those two electrodes together. Why? Well, in fact, in order to create a field, you would charge the capacitor at the beginning so that you will position positive charges on the upper electrode and negative charges on the lower electrode. So those two charges would now be there. Now if we would like to find out the force attracting those two electrodes, we would have two possibilities, at least. The first could be, well, any of those charges on the upper electrode attracts any of those charges on the lower electrode. Well, the slight problem is that we can find out the force, but in that case we would have to, for example, find out this force and add all of them together. It is possible, it's workable, it's a lot of work to do. Then, isn't there another way how to find out the force that affects? Well, we have already known that the force is given by the charge multiplied by the field strength. Well, in this case, we have some charge on the upper electrode, we have some charge on the lower electrode. Could we somehow attach into one equation electric field strength and the charge density on the electrode? Remember, we have been talking boundary conditions, and one of the boundary conditions directly stated that the normal portion of electric flux density dN could be connected to the density of the charge on the surface. So we know that those two are equivalent things. Those two ones are equivalent. Okay. But we do have to establish the normal component of the flux density. Well, in the case that the material in the capacitor is isotropic, the direction of electric field of both components of electric field, I mean electric flux density and electric strength, are identical, they are collinear, then we could put down that E multiplied by permittivity, which is D, is equivalent to the charge density on the surface of the electrode. Now we know the electric field strength. It is the voltage divided by the distance between electrodes. We know the permittivity, that depends on the material, and we have obtained the charge density. So, for each square meter of the surface, we have a charge of charge density multiplied by 1 square meter. Or we can say the pressure at any point of the electrode is given by a multiple of charge density and electric field strength. So the pressure, small p, would be E normal multiplied by the charge density, but the electric field or the charge density could be derived as electric flux, which is equivalent to the charge density. So we can get this by E epsilon, and then we get E squared epsilon as the pressure on the electrodes. And we know that the E is the voltage divided by the distance, which is V squared over distance squared multiplied by permittivity. Now this is the pressure which is exaggerated by the field on the electrodes. Just don't be fooled. The lower electrode is pulled up, the upper electrode is pulled down. There is no force that would result in a movement of the capacitor. At least once a year I receive an email from somebody who has invented, please put that into proper sense, who has, or he thinks that he has invented a flying device that would be created by several capacitors charged. He somehow thinks that it can pull itself upstairs. It's a nonsense. Those two forces are identical as to the magnitude, but they are opposite direction. So we would get no force affecting the whole capacitor. But yes, charging the capacitor means bringing mechanical stress into its construction. This would be very low for small signal capacitors, but with high voltages you can get quite a lot of mechanical stress during the fact that those two electrodes attract each other, and that pull would increase quadratically with the voltage, as mostly the position of those electrodes would not change. Your questions, please. So first, there are no questions to this. Second, I have received a message from Gadliauskas Davidas, sorry, I need different glasses to read it properly, which is correct to my last question. And just, do you know where the mistake was? So what should have been here is a squared, and this is the mistake. I would like to thank the colleague that he has read carefully, and I will add a second task for you, which again would be a competition. The second competition would be for some real prize for those who don't, for those who are not against that. For those who drink wine, that would be a bottle of good wine. For those who do not drink wine, we have to agree that would be a bottle of a good tomato or orange or other juice. But now the competition question. Let's get back to charged balls. We have 3 charged balls. All of them have very small diameters when compared to the distance. Now, the arrangement has an X of symmetry, and those 3 balls are situated so that this distance which we call v, small v, is the same as the height of the triangle. So this is v. We have those 3 charges symmetrically placed, and the X of symmetry is the coordinate of z, and the 0 of the coordinate starts here. So we measure z out of here. So we have 3 charges. One of them is positive, and the 2 down are negative. So we have 3 charges, this, and this. Now we want to find out all positions, all places on the x, z, so on the X of symmetry, where the field vanishes. That is, where the electric field strength created by those 2 negative charges is of the same size but opposite direction than the field created by the positive charge. So those 2 negative, which are here, can compensate for that positive one, and at some value of the coordinate z, there would be no electric field, no electric field strength, no electric flux density. To make the things simple, those 3 balls are of negligible radius against the distance. So let's treat them as point charges. Now, as far as I know, the solution of this task is nowhere in the textbook. So it's a challenge for you to find out the result. I bet a bottle of wine on that, a good wine or good juice, for the winner. The winner is the first one who sends me a correct solution. But please bear in your mind that there is not only one location with zero field. You can easily guess some of them, while the others need some computation. So my question is, where would the field be zero in this system? And my hint is, yes, it will be on the x of symmetry. So don't try to find it here or there. On the x of symmetry for some value of z, there would be zero field. And the task is to find where. Now I'd switch to something which is very important in circuit theory and which is a kind of parallel of capacity, and that's inductance. Now the inductance is something which has several definitions, and we should point a focus on that to understand them properly. The first and simplest definition of an inductance is called static definition. The inductance is mostly denoted by L and the unit is Henry. But what this static definition tells about inductance? Well, it says, well, it is a ratio between magnetic flux and the current that has created it. So it's a ratio. In numerator we've got magnetic flux, and in denominator there is electric current. To make a small illustration how to find out the inductance, let us consider a coaxial cable. A coaxial cable is something that is very widely used to transfer signals, at least the feeding cable for your TV set, from the antenna to the TV set or set-top box. It's a kind of coaxial cable, and then the main reason is that the magnetic field and the electric field is kept inside the cable, and therefore it's not very affected by moving people around, for example. But now let's find the inductance of a cable. The cable, if it's straight, may be considered endless, which is not a good idea to find out a property of something which is not bounded at the end. So let us find the inductance of a 1 meter section of the cable. Now I am talking about coaxial cable. How does that look like? Well, it's an inner conductor, which is a metallic cylinder, and on that you have a sheet of dielectrics, and you have a very thin outer conductor, and this is the cable. Mostly this conductor is connected to ground, and this conductor is the hot conductor. So let's say that we have the coaxial cable with two concentric cylinders that are mutually insulated, and there is a current that flows through the inside conductor there, and somewhere there at the end is the consumer, the load, and the current returns back through the outer conductor. By the way, a coaxial cable has been first used at the beginning of last century, and the first important work describing the properties like the capacity and inductance per 1 meter and resulting impedance has been published in Bell Labs journal sometimes in 1924. And this paper has remained the only important paper on that for a long time, and the real wave properties have been investigated then by Wade from National Institute of Standards and Technology from Boulder, Colorado, as late as in 1996. So, and still this was a kind of idealized cable. So something that has been revolutionizing electric circuits, something that's very widely used, is not still fully theoretically described. That's something like the steam machine, which has changed the industry, and the full physical description has emerged 100 years later. So there is still something to do. If you want a good topic for diploma work, that could be a coaxial cable. Now we will go on with the inductance. So where the magnetic field inside the coaxial cable comes from? Well, we have the conductor inside, which creates a magnetic field, a set of concentric cylinders or lines. And in order to find its flux, we would have to get an integral of flux density over a proper surface. Now, the simplest way how to find out the surface is a radial section from the inner conductor to the outer conductor. Why a radial one? Well, first, all the flux lines are perpendicular here, so you will find it easily. Second, it is the shortest way for integration, and it directly runs from the inner conductor radius to the outer conductor radius. So to name it somehow, let this is small a, let this outer conductor radius is b. So we have the inner conductor with the radius a, the outer conductor with the radius b, and now we would like to find out the magnetic flux that flows through 1 meter of that line. So let's first find the magnetic flux density. Well, we have, out of the Ampere's law, we have established the equation which says that the H is I over 2 pi r, where r is the distance from the center of the coaxial cable. Now, if we want to make an academic point, there is some flux running through the inner conductor. We will neglect it now because most applications of the coaxial cable use high frequencies, and we will learn later that the current only flows on the surface of the conductor. We will return to that case later to find out the remaining portion of the magnetic field. But at the time being, we have this equation for magnetic field, and to find out the flux density, we have to multiply that by mu, which is the permeability. So the flux density would be I mu over 2 pi r. And that holds for the inner part of the coaxial cable. So now we would have to integrate this over a surface which is radial and in that direction long for just 1 meter. Then, in fact, we have to make an integral of b multiplied by 1 meter from a to b dr. So the flux phi would then be, I put here 1, just to say we integrate for 1 meter of length. Integral from a to b is mu I over 2 pi r dr. And this is a textbook integral. This, and this is a constant. We move it ahead of the integration. And we have an integral of 1 over r dr, which gives us the logarithm, the natural logarithm of r. Putting in the upper and lower bound, we would get an equation for phi, which is mu I over 2 pi natural logarithm of b over a. So now we have the flux that flows through a 1 meter long section of a coaxial cable. And we can return back to the definition of inductance. Its ratio. In the numerator we've got the flux, in denominator we've got the current that has created the flux. And therefore, to get the inductance, we just divide the flux by the current. Fortunately, it's a semi-proof of correctness of our calculations. The current in a linear system must cancel out. If not, we must have made a mistake. But in this case, if we divide this by current, we receive the inductance of a 1 meter long section equivalent to mu over 2 pi logarithm b over a. Now this value is first a value of an inductance that we have established. Second, we will keep it somewhere in our memories because this is an important value for establishing the impedance of a coaxial cable. If you want to buy some, there are produced cables with different property called impedance, and we will need some time to find out what that does mean. But anyway, it's possibly the most important property of a coaxial cable. And it is closely related to capacity per meter and inductance per meter. So this is, we have established our first value of inductance, and that's a good time for question. So your questions to this example.
Can you please remind where B and A is, because it's difficult to see?
Okay, so B is numerator, A is denominator. How that has happened? Well, first we had the integral, which was from A to B, from inner conductor to outer conductor. We have been integrating through the whole path to catch all the magnetic field. Now, after carrying out the integration, we had some constants and we had a logarithm of r, because the integration variable was r. So we have the logarithm of upper bound minus the logarithm of lower bound. That would be logarithm b minus logarithm a. The difference between logarithms could be expressed like the logarithm of a ratio. So we arrive to logarithm b over a. Is that clear now?
Actually, it was clear. I just asked where are they located in the scheme.
Yeah. So, have I replied?
Basically, yes.
Yeah. Please don't hesitate to ask questions because everything is in books. You just can't ask a question to a book, but you can ask a question here. Okay, so we have the simplest definition and the simplest case to find out inductance. Now, I will complicate the case a little bit. I will first put down 3 definitions of an inductor. You have possibly already been exposed to circuit theory. For people doing circuit theory, an inductor is a black box with 2 terminals. There is some current running through,